Welcome back to the last part of this lecture on natural language processing. So this part here will concern what is called the transformer representation, which one could say is the current state-of-the-art representation of words and documents. So the transformer representation, the idea is to extend the word-to-vec and fast text embeddings that we saw previously in the last part by also incorporating the context. So we quite like all the positive properties that the word-to-vec and fast text embeddings have. So we want to maintain all of those while also incorporating the context. So by here, the context, we mean the words occurring in the document. And this would mean that our word embeddings are now dynamic, which means that we might have a different word embedding for the word apple depending on the sentence it appears in, because we want apple, the fruit, to have a different word embedding compared to Apple, the company. So taking this context into account is achieved through a mechanism called attention. So let's go through that. So more specifically, this particular kind of attention, because attention is a more general concept, this attention is called self-attention. So what we do is that we start with a term T, and by term here I mean any piece of a document. This could be a word, this could also be a part of a word, it could be individual characters, but for the sake of simplicity we can just think of T and terms in general as words. Right, so we are given a term T and it's appearing in a document D. What we're interested in is we want the representation of T to take all the words in the document into account. So the first step that we do is that we embed all the terms in D, resulting in some embeddings. This could be done via a word-to-vec method, but we will see in the transform architecture that we do it slightly differently, but we produce some kind of embedding for all the terms in the document. Say for the sake of simplicity that T is in fact the first term, so that it's associated with the first embedding. Okay, so the next step is then to compute the dot product between E1, so E1 is the first embedding associated to our term T. Compute the dot product between this E1 and all of the embeddings E1 up to En, resulting in some scores which we label alpha 1 up to alpha n here. So alpha 1 is the result of E1 dot producted with itself. Alpha 2 is the result of E1 dot product E2, and so on. So if we assume that the embeddings that we get up from step 2 here, if we assume that they are all normalized, then this means, for instance, that in our example that alpha 1 is just equal to 1. Right, so next step is then to apply a softmax to the scores, which would yield us weights. So this softmax is the same thing that you've seen previously with neural networks, and it's just a function which converts all these scores, which could be anything. They could be negative, positive, really large, really small, and convert that into probabilities between 0 and 1, which all sum up to 1. So we now call these weights, or you could call them attention weights. It's quite common as well. W1 up to Wn. Right. So now, from this term, we now have a sequence of probabilities for each term in the document. So this is quite important because now these weights represent how important other terms in the document are to the representation of T. So if T was the word apple, for instance, and some of the other words were business-related terms like profit, then those words would have a high weight because they would contribute to knowing that T, word apple, is referring to the company Apple rather than the fruit apple. Right, so the final contextual embedding for T, because right now we just have a bunch of weights, we need to combine them somehow. The contextual embedding for T is then the weighted sum of the embeddings by the weights. So all we're doing here is just take every embedding, so we take embedding number 1, multiply by weight number 1, plus embedding number 2, multiply by weight number 2, plus, and so on. So this is the same thing as just the dot product between the W vector, this vector here, with the embedding vector here. So this results in a resulting embedding. Okay. So there are many different types of attention. So I mentioned self-attention is a particular kind of attention, but there are even many different kinds of self-attention. So this one in particular is called dot product attention or dot product self-attention, because what we're doing when we're building the scores is that we are just taking dot products. So we could have done this in different ways that would have resulted in different types of self-attention. So this is also the simplest kind. So this graphic is just the same thing, just trying to visualize it, like the thing that we just saw. So we have an example here of I really liked Ali Smith's new book. This time I've decided to split Smiths into 2 different terms. So we just have a bunch of terms here. We have the embeddings for all of the terms, so with dimension D. So what we do firstly is that we compute all of these dot products, like all of these scores. So alpha 1 would be the dot product of this vector with itself. Alpha 2 would be these 2 vectors multiplied by each other, dot producted, and alpha 3 and so on. Then we take the softmax and arrive at all these W values, and then the W's are combined with the embeddings, of course, to one resulting contextual embedding for the word I. Okay, and we do this for all of the terms. So this would only give a contextual embedding for I. We have to do the same to produce one for really, the same for liked, and so on. So you see there's a quadratic complexity going on for just to produce this one vector contextual embedding, I had to look at the entire sequence of terms in this document. And I would have to do exactly the same when I'm computing the contextual embedding for the word really. So the complexity of this attention mechanism is certainly quite large, so it would take up a lot of memory, which is usually a problem, or can be a problem when dealing with these attention mechanisms. Okay, so a transformer representation is almost the same as a stack of dense layers that we've seen in neural networks. So these are just matrices followed by self-attention layers. And when I say a self-attention layer, I just mean what we have just seen, that we start with a sequence of embeddings for every term, and then we combine those, or we transform those to contextual embeddings for each term by using all of these scores and weights. So the only difference is between just having a stack of dense layers and attention layers and the actual transformer encoder is that we need to somehow encode the ordering of the terms in our document. So we won't go into that here, but just keep in mind that there is a static positional encoding. It's just a function that takes in indices and spits out trigonometric functions, or a combination of cosines and sines that somehow save or store the position of the individual terms. So we just note that this positional encoding is added to the individual representations to have that into account as well. So we start with the term embeddings, then we add the positional encoding. So this is just a black box for now, that's fine. So we just add these two together. Then we pass it through an attention layer, then we get contextual embeddings. Then we pass it through a dense layer with an activation function like relu, for instance. We repeat this cycle n many times, where you can set n to be whatever you like. It's usually set somewhere between, say, 5 and 20. I think the common ones in the original paper, or the one used in the original paper, was 6, but since then I think it's been improved, well, extended to 12 and perhaps also 18. Anyway, we do this a bunch of times, and then we end up with a contextual embedding. So this is of course just the encoder layer. So this is the analog of the encode thing that we saw when we were computing word-to-vec methods. To be able to train this, we need a decoder as well, but I won't go into that here. Just if we happen to have a transformer model which is already trained, these are the layers that we have to go through to arrive at the contextual embedding. So there's a point here on tokenization as well. So before with fast text, the fast text algorithm, keep in mind or recall that fast text was the same thing as word-to-vec, but the main difference was that instead of splitting up by words and embedding those, we split up by character engrams and embedded those separately. So you can do this splitting up in various different ways. You can do this character engram, but you could also split up words based on some other rule. Like we saw in the previous example, for instance, that I split up the word smiths, like S at the end, to splitting those up into two words, to have smith and then have the apostrophe S as a separate word or separate term. So it's a whole field as well to come up with efficient and good tokenization. And this is what this process is called, the splitting up of words or of documents in general. Is called tokenization. The tokenizers which are employed in modern transformer models are learned on data, and they are based on subwords. So I have an example here where usually the word would be split into the subwords usual and also the word ly. The reason for this is that if you can get a really good representation of ly, you can suddenly attach ly to many different words and preserve the same meaning, rather than having to relearn it for every ly, every adverb almost in English that you would come across. So it's about efficiency as well. So yeah, and they are learned from data. So we won't go into the details of how these are learned, but if you're interested, you can search for byte pair encoding or word piece tokenization. They are very similar, those two, and are both used in modern transformer models. They just have like small differences, but you can look at both. Second point I want to make is transfer learning. So we notice that these models are really quite large. Like I mentioned that we had to repeat the dense layer and attention layer 6, 12, maybe even 18 times, and that's just the encoder. We have to go through a decoder as well of the same size. So training a good transformer model requires a vast amount of data. So this could be millions or even billions of documents. So it means that it would be highly inefficient if every time we just had a simple text classification task and we wanted to have a very nice model that could perform well on that, we would suddenly need millions or even billions of documents just to perform this simple task. So that would be highly inefficient. And also from a climate point of view, training these large models, they have severe consequences for the climate. So we want to train as few of them as possible and reuse them. So an example here with a link to the article, that training just one model can emit as much CO2 as 5 cars during their lifetime. This is even a model that was quite old by like machine learning standards, and the more newer models, they are way worse. I wouldn't be surprised if you had to 10 double this CO2 emission. So we really don't want to train many of these models. We want to train as few as possible. So to combat this, there's this paradigm, transfer learning, which is really not that new, but it's just become very popular with these transformer architectures. It's a way of reusing a massive model for any language task, such as classification. So what the idea is that you have to train one of these transformer models on massive amounts of data, which is usually done by the large companies or organizations. When you have that, then you can do what is called fine-tune such a pre-trained model on a particular task. And what this means is that we have the model and we have already trained it, so all the weights are fine-tuned, all the weights in the individual neural network layers. What we do then is that we add a new final layer to this pre-trained model, which projects the outputs to the number of classes we're interested in. If we're doing, say, a binary classification task, then we would project down to 2 dimensions or 2 classes. And what we then do is we train the entire model for a small amount of time on a very limited amount of data. So visualization here is we start with the term embeddings. We pass them through transformer, which has pre-trained weights. We have added a new dense layer up top, which is randomly initialized. Then we add a softmax, and then we get some class probabilities. So we only have to train this network here very little on little amounts of data, because it can reuse all the knowledge it has learned in these pre-trained weights. Okay. So to go back to our checklist, the transformer representation, it has all the same features as the fast text one, which it does scale words according to their rarity, captures correlations between words, and can handle new words that were not present in the training data, because we're doing a more efficient way of tokenizing rather than simply tokenizing by words. And finally, what we achieve is contextual and contextual embedding for each word. So representation becomes dynamic, that Apple the fruit is represented differently to Apple the company. These embeddings, transformer embeddings, are usually the most powerful, especially when using transfer learning. It doesn't very rarely make sense to use a transformer model from scratch. You would want to pull down a pre-trained model. Thankfully, that has been made way easier in newer times, and we will see some of that in the exercise notebook. So a little tip towards the end here. So we looked at many different ways of representing text in NLP. Usually a transformer, pre-trained transformer embedding will yield the best performance, but keep in mind that it's also the most resource intensive. Even just to fine-tune a pre-trained transformer on a simple task, you would usually require GPU power for many hours still, even then. And when you use it for inference, it might be way slower than some of the other embeddings that we have seen. Sometimes a TF-IDF embedding can perform just as well at a fraction of the compute cost, and training is really fast as well. So just keep that in mind. Not that you shouldn't use transformers, but you should just use them wisely. If you are working with a very simple task, maybe it doesn't make sense to use a pre-trained transformer in that case. So don't blindly use them, and even if you do use them, it does make a big difference which pre-trained model you use. There are many thousands of pre-trained models out there, so just keep that in mind as well. So to conclude this last part, transformer models, they are the modern architectures which can create word representations. They take the context into the word into account. So that's the main difference between these embeddings and representations and the previous ones that we've seen. Training transformers can take up vast amounts of resources. So we usually have to use transfer learning techniques to apply these transformer embeddings. And the embeddings tend to be the most powerful, but for simple tasks, the TF-IDF model can still be better. Do not blindly use a transformer model. And lastly, we have some references here. There's a tutorial notebook on the transformer architecture on this annotated transformer blog post. There's the original paper, Attention is All You Need, which introduced the transformers architecture in 2017. And then there's the documentation for the transformers package by the Hugging Face startup, which enables very easy to use transfer learning in your concrete applications. And that's all there is. Thank you so much for your attention.